In this video, we're going to review how to simplify radical expressions. There are four aspects of this. When we talk about simplifying radical expressions, primarily we're talking about this one, which is basically to take all the the perfect squares out of the square roots and then only leave irrational numbers behind. And I'll explain what I mean further. And then the rest of it, these four operations, add, subtract, multiply, and divide, is all operations eventually have to boils down to simplification of the radicals. So like these examples here, there are some numbers. Here's a square root, and inside the square root I have a 12. And I need to find the perfect square in 12. Now, there are several ways of finding perfect squares. One way is to do the factor tree. So you can do 2 times 6, and then 6 obviously is still not a prime number, it's an even number, so there's a 2 in there, and then 2 times 3 gives me 6. And then you can rewrite this expression as 12 equals, you pick up all the terms at the end of each of the tree branch. For example, you do 2 times 2 times 3. And that way you're avoiding non-prime numbers. As you can tell, 2 times 2, that's a perfect square. I've got 2 squared times 3. Now, if I have this perfect square inside the square root, I can take the 2 out. I can take this base out and then cancel the entire term inside. But I still have this 3 left behind. So 3 is not a perfect square, so that leaves there. So 2 root 3 is the answer here. Okay, another example, square root of 36 can be rewritten as the perfect square of 6 squared. And therefore, the 6 comes out, everything else goes away. Square root of 32 can be rewritten as square root of 16 times 2. We know 16 is 4 squared. Therefore, the 4 comes out because this power of 2 and this root 2 cancels. The 4 comes out but leaves the 2 behind. Square root of 20 is the perfect square inside is 4 times 5. 5 is a prime number, nothing you can do about that. 4 is the perfect square of 2, so that comes out. If you want to rewrite the 4 into 2 squared to see how the power of 2 and the square root, this 2 cancels, and then the base 2 comes out. Let's do something with, let's do number 9. Number 9, in this case, I've got variables. Now, it doesn't matter if it's variable, it's number. We all have to rewrite this into perfect squares. So if I factor 80, eventually I can do 16 times 5 equals 80, and then m squared. Notice that 16 is 4 squared. That's my perfect square. 5 is just a prime number. I can't do anything about it. Okay, up till this point, all I did was I rewrote this. I still have 80m squared inside, but I just rewrote it to make it easier so that I can see my perfect square here is right here. So the 4 comes out. I've got another perfect, so this term is gone. 5 stays, but look here, I've got a power of 2. Therefore, this root 2 and the power of 2 cancels, the base m comes out. And if I further simplify that, I should have negative 12m root 2. Okay, so let's do something a little more challenging. Let's look at number 8. Number 8 here, I've got 4 times 72. I know 72 can be rewritten as 36 times 2. Oh, there's a v in there, sorry. And therefore, it's 4 times 36 is 6 squared times 2 times v. That's my square root there. Now my perfect square comes out, so I'm going to do it here. My perfect square, the base is 6. So 6 comes out, these gets canceled. What's left behind is 2v. There's no more squares. There's no more perfect squares in 2v. So it stays inside. 4 times 6 is 24. Okay. Let's look at number 7. I've got 2 here. And 343 is a little bit more challenging. But if you divide it by 7, you will find it's 7 times 49 times r raised to the 4th power. Here, I know that 7 stays, 49 is 7 squared. Here's the tricky part. R raised to the 4 squared. Is there any way I can rewrite that into R something something squared? And here triggers another property, which is, I'm going to write it here. A raised to the m, and then raised to the n again equals a raised to the m times n. The example of that is 2 squared cubed. What this is saying is that if I do this in the tedious way, 2 squared is 2 times 2, right? That cubed, meaning 2 times 2 times 2 times 2 times 2 times 2. Oops, 2 times 2. Right? So that's 1 time, 2 times, 3 times. That's what that cubed means. Let's see. That means 1, 2, 3, 4, 5, 6. I have 2 raised to the 6th power. So that's an example when you have something raised to something a raised to a power, and then the whole thing raised again. You just multiply the m and n. So the reverse of that is true. If I have r raised to the 4th power, I already know I want a perfect square there. So 4 divided by 2 is 2. That's how I got this r2 here. So now if I continue with that, I will have 2 times the 7 comes out, the r squared comes out, r squared, and then inside is just root 7. So it's 14 r squared root 7. And generally you actually write it in this way, 14 root 7. That's just a habit. You put the numbers together and put the variables together. Okay, let's look at number 10. I have negative 4. I'm not touching that. 155. I think it's 15 squared is 155. And if you're not sure, let's see what we can do. There's definitely a 5. 5 times 35. Oh, maybe I am wrong. 35, that's right. And then there's another 5. Oh, I was wrong. So it's not 15 squared. Then let's get rid of this part. So this is 5 times 5 times 7. So 5 squared times 7 times m raised to the 4th power. Again, I want to write that into something squared. I use 4 divided by 2. I have 2. So negative 4 times the 5 comes out. The m squared comes out. Be careful, it's m squared comes out. Root 7 is left behind. 4 times 5 is 20. My final answer is it's negative 20 root 7m. Okay. Let's try this one. Let's try a harder one. So now I have I'm going to erase something here so that I'm going to bring this over here using a different color. So I have, this is number 11. I have 3 times square root of 343 m raised to the 3rd power n squared. So the first thing I notice is n squared. So I can just take the n out, right? And then 343, we said that can be rewritten as 7 times 49. Now, in this case, I don't have an even number, so I cannot use this property, because if I want it to be 2, I don't know which number divided by 2 can give me 3 without going into a fraction scenario. So what I'm going to do is, because it's m cubed, I'm going to rewrite it into m times m squared. I still have m cubed here, right? But I took one m out. I left an m with a square in there. Now, this 49 is 7 squared, so that 7 can comes out too. 49 disappears. This m can come out because I have a square there. So m comes out. That disappears. What's left behind is 7m. If I clean that up, I would have 3 times 7 is 21. I'll put the m in the front, m times n, and then I still have 7m. If you want to write it even prettier, make sure the m is inside. You would have 21 root 7m. This is pretty tedious, but the point is, if you have even number, you can use this property. Okay? If you have odd number, take one out to make the other term even. And that way you would have your answer here. So I didn't do this couple of ones. I just want to leave it for you to practice. Second topic is, how do we add and subtract radicals? This is basically like algebra, treated almost like treated like a variable. You can only add or subtract if they are the exact same variable. So 3 root 3 minus 2 root 3 is just 1 root 3. That's it. Okay? And then, but look at the rest of them. They don't have the same radicals. So there we have to use the skill we just practiced. We have to factor it, and hopefully I will have a root 5 here. So let's see if I can do that. 45 is 9 times 5. 9 is 3 squared. I'm skipping a step there. Right? 9 times 5. 9 is 3 squared plus 2 root 5. So in this case, I have 2 here. 3 comes out because of the square. Root 5 remains plus 2 root 5. 2 times 3 is 6. 6 plus 2. I have 6 root 5 plus 2 root 5. I should have 8 root 5. Okay. Let's factor this one. So negative 2, the perfect square in there is 9 times 2 minus root 2. And negative 2, 9 is 3 squared, so 3 comes out, 2 is left behind. I have negative 6 root 2 minus root 2 root 2. I should have negative 8 root 2. Okay, again, all of these simplifications are the same skills we just practiced in the previous page. And then the rest of it, just treat the radical like a combine like terms, basically. Multiplying, here, these actually requires me to distribute. So an integer times a radical, nothing you can do, just do that. And radical times a radical, you want to combine the radicals. So now I have 4 root 5 plus root 10. Root 10 is, there's no perfect square in root 10, so we're stuck. This is the final answer, and this is perfectly legal in high school. No need to convert it into a decimal point. Again, distribute. Root 2 times root 2 gives me 2. Root 2 times 3, it's just 3 root 2. Distribute again. Negative 2 times negative. Double negative makes a positive. 2 times 1, right? There's an invisible 1 here, so that's positive 2. And then 3 times 10 is 30 plus root 3. 30, do we have perfect square in 30? I don't think so. So this is it. We're done. I'll leave 24 for you to play with. Dividing. dividing, I'm going to start with the lower half. These are a little easier. There are several ways of doing it. You can do, you can combine, so you can treat this as there's an invisible 1 there. So it's 1/4 comes out, then root 16 over root 4. Root 16 over 4 can be rewritten into 1, just like multiplication. They can be under the same radical. Now that gives me 4. 4 happens to be a perfect square of 2. So 2 squared, 2 comes out. Now I can further simplify that into half. 38, same thing. I can combine it. So if I cancel it by 2, I have 3 here, I have 16. There's no more I can do. So now I'm going to rewrite it, separate it again after I combined it. The reason I do that is because it's illegal to have this format, because I've got a radical, as you can see, I've got a radical in my denominator. And to get rid of the radical, I just need to multiply root 16 over root 16, because this way allows me to take the 16 out. Remember, this is a multiplication. We can simply do combine the houses. I have 16 squared, therefore 16 comes out. And over here, I have 3 times 16. 3 times 16 is 48. 48, I believe, has some radicals in there. I'm sorry, has some perfect squares in there. 48 can be rewritten as 16 times 3. So 16 obviously is 4 squared. Therefore, the 4 comes out, 16 disappears, root 3 remains. I can further simplify this. My final answer is 5 root 3 over 4. It's a simple problem, but you have to do the division first. And then after you do the division, you separate the radicals, simplify the denominator by getting rid of the radicals, right? And then once you do that, you have to go back and simplify this again, and then keep canceling until you have an irrational number in there. I'll leave 39 and 40 for you to do. 31 through 34, we didn't discuss it in class. This is more advanced. Notice that there is a radical in here, but here I cannot just multiply the radical. I cannot do 4 root 3 or even root 3 over root 3, because if I do that, notice that I will get rid of this radical here, but I will add root 3 to the first term. So that mess is not going to help me, right? So I have to do something. And you're going to learn this more in Algebra 2. It's called conjugate. So in other words, here I've got an integer minus a radical. Rather than multiplying just one radical, I multiply the conjugate. The conjugate meaning if this is a plus b, its conjugate is a minus b. The reason I do that, and let me do this. So it's 5 plus root 3 over 5 plus root 3. So this is a 1, isn't it? So I'm not changing my original expression. It's that multiplied by 1. The reason that I do that is because of this property. A plus b times a minus b equals a squared minus b squared. So now if I multiply these two together, I would have a squared, which is 5 squared, which is 25, minus b squared, which is 4 squared, which is 16, and root 3 squared is just 3. Now, see, I all of a sudden got rid of the radical, and upstairs I have to distribute the 5. 5 times 5 is 25, plus 5 times 4 root 3 is 20 root 3. So now I have, upstairs I have 25 plus 20 root 3. Downstairs, I have 25 minus 48. 25 minus 48, I would end up having a minus, and it's minus 23. So that's the answer. Okay, this is more evolved. We're not testing you this year, but it will come out in Algebra 2. So I will not solve this one just to keep this video short, but I want to set it up for you. So you multiply, you multiply the conjugate. A plus B becomes A minus B. And make sure that you make it the same in the numerator and denominator so that you don't change my original value. Once you have A plus B times A minus B, in the denominator, you would have root 3 squared, which is 3. 3 root 5 times root 5 is 9 times 5, it's 45, right? So upstairs you have 5 root 3 times root 3, which is 5 times 3, which is 15. 5 root 3 times 3 root 5, so that would give you 15 root 15. I might as well just solve this. I've gone this far. So I'm just copying down the numerator, and then I will simplify the denominator. It's negative 42. Now notice I can cancel by 3. I would have 5, 5, 3, I would have 14. So my final answer is negative 5 plus 5 root 5 over 14. Okay, so these are just some more challenging ones for you to practice, but you really need to know how to solve these ones at the bottom. So to recap, the first thing we reviewed is simplifying radicals. The way to simplify it is to multiply a radical over a radical so that you no longer have radical inside. But before you do that, you want to factor it as much as possible. Adding and subtracting are easier. They're like combined like terms. You can only subtract the same radicals. If it's something that's not fully simplified, you need to simplify it first, and then that will give you, I think this is 2 root 2 as well, that give you 4 root 2. Okay, multiplying radicals are easy. If I have 2 radicals multiplying each other, I just put them together inside one radical. Same thing with dividing radicals. Root 16 divided by 4, I can do this. And I just further simplify this. Okay, so that's a quick review of radical expressions. Let me know if you have any more questions.